Okay, the first problem here, the free vibration responses of an electric motor of weight 500 Newton mounted on different types of foundations are shown in figure A and B. Identify the following in each case: the nature of damping provided by the foundations, the spring constants and damping coefficients of the foundation, and the undamped and damped natural frequencies of the electric motor. So for case A, here you can see the part 1, we want to obtain the nature of damping. So we can compare part A and B. For part A, to obtain the nature of the damper, we need only to look at the amplitude and how it decreased. It decreased by time. Here, for case A, you can see the first amplitude is 8, then it decreased to 4, it decreased to 2. So the amplitude in the first step decreased by 4, in the next step decreased by 2, and in the last one is decreased by 1. So it's decreasing exponentially, it's not linear, as you can see. In the second one, in part B, the amplitude is 8, then it's in the starting of the second cycle it's 6, and in the third cycle it's 4. So in the first cycle it's decreased by 2, in the second cycle is decreased again by 2, and so on. So here you can see the decrement is linearly. So the part A, it's a viscous damping. This is a viscous damping. But in the part B, because it's decreased linearly, it's a column damping. So we have the nature of each of them. For the first one is viscous, and for the second one is column. So this is a part 1. For part 2, we want to obtain the spring constant and damping coefficients of the foundation. The damping coefficient for this one, it's clear. When we deal with a column damping, you need to only obtain the natural frequency, and then you can easily obtain the the stiffness and the mass of the system. So here you can see for both of them the period is 0.2, as you can see for both cases. So from this you can easily find the natural frequency for the column damping is 31.41 from the period. But for the first one, it's not that easy. I mean, we can find the period of damping. Here you can see we use a D. It means this is the period of damp system, and it's equal to 0.2. So the frequency of the damp system is 5 Hertz. And finally, omega D, or the natural frequency of the damp system, is 2 pi times by F, and we can convert it into radian per second, and it's equal to 31.41. So in case A, this is the frequency of the damped system, but in case B, this is the natural frequency of the system, because it's not a damped, it's viscous damped system. And as you know, the frequency, the natural frequency of a system in with column damping will remain the same. So this is the natural frequency for case B, but for case A, this is the damped frequency. Also, we need to calculate the damping ratio. The damping ratio will be obtained from the delta, or the logarithmic decrement. Here you can write the delta equation for 2 consecutive cycles, and it's equal to 8 divided by 4, or 4 divided by 2, and you can obtain ln of 2, which is 0.693. This is the delta, and then from this equation you can obtain the damping ratio, which is the quotient or the relation between delta and the logarithmic decrement and damping ratio. So you can substitute for delta and obtain the damping ratio, which is 0.109. And now you can find the natural frequency, because this is a damped system. The natural frequency of the system is equal to the natural frequency of the damped system divided by square root of 1 minus psi squared, which psi is the damping ratio. Now we can substitute. So the natural frequency of the first system in part A is 31.6. And now we can find the stiffness, which is m times by omega n squared. And m is 31, omega n is 31.6 here. And m is 500 divided by g, because the weight of the system is 500 Newton. So the mass is 500 divided by g. And this is the stiffness of the foundation. And also we can find the damping, viscose damping constant, which is equal to 2 times by m times by omega n times by psi. We have m, we have omega n and psi, and we can obtain c. But for part B, to obtain the stiffness, you can use this equation, but this time instead of omega n, you need to substitute 31.41, because as I told you, the natural frequency in case B with foundation B is the same as the undamped system, and it's equal to 31.41. And here instead of 31.6, you need to substitute 31.4. So you can find the stiffness of the system. Okay, any question? Is it clear?
Yes, sir.
Okay. The question 2, we need to derive the equation of motion for different systems and find the natural frequency. Part A, we have a horizontal structure. We have a cylinder located on a surface which is rotating without slipping. We have a pure rolling. The cylinder has a mass of m, a radius of r. We need to extract the equation of motion for this system. You can use the Newton's second law, because here we have damper. We cannot use the energy methods now. Of course, in the, I think in chapter 3 or 4, I'm not sure. In later, we will use another method, method in energy, which is called, I think, Lagrange. We will use that method to extract the equation of motion for this type of system when we have damper, because when we have damper, it's not a conservative system. The energy will be dissipated in this structure, so we cannot use the previous method of energy, and we need another correction on our method. So here for this system, we use the Newton's second law. For this purpose, we can find, or we can write, in fact, the moment equation about this point O, because from dynamic, you know that when we have pure rotation, pure rolling, and we don't have slipping in our motion, it means that any question?
No, sir.
Okay. Because you're typing here and I cannot understand what do you mean.
No, the other guy is not able to listen to your voice, but I am able to listen to your voice.
Okay. So maybe the problem is from his side.
Yeah.
Okay. So when we don't have a slipping, it's we can assume that the motion is a pure rotation about point O, and we can assume that point O is a fixed point of rotation, and this cylinder is rotating about this point. So we can write the moment equation about point O, similar to the previous example in the lecture, that we had one rigid bar which was rotating about a fixed point. Here we can assume that this cylinder is rotating about this point O, and for this moment we can extract the equation of motion. So for this purpose, we can write the moment equation about this point O. It must be equal to the mass moment of inertia about point O multiplied by the angular acceleration, which is called theta double dot. So in this equation, we can plot the free body diagram. We will have two reactions of force here at point O, but we neglect them because when you write the moment equation about point O, they will not appear into the equation. and we have one force due to the spring and one force due to the damper, which is Cx dot, and X is R times by theta, and IO, which is the mass moment of inertia about point O, and it's equal to the mass moment of inertia about the mass center for the cylinder, plus m times by d squared, which d is the distance between the mass center here and the point O, which this distance is equal to r in this case. So IO is equal to 3/2 times by m times by r squared. As I told you, is x is equal to r theta, so we can substitute and simplify. So when you write the moment equation, the force kx times by its arm, which is r, this distance, and the force cx dot times by its arm, which again it's r. So we will have minus kxr minus cx dot r, and this minus is due to the negative direction of the moment created by these forces, and it must be equal to 3/2 times by mr squared theta double dot, and we can extract the equation of motion. So this is the equation of motion, and the natural frequency of the system is a square root of the coefficient of x divided by the coefficient of x double dot. So you can calculate omega n. Is it clear, this one? Yes? Yes or no? If you need more clarification, please let me know. I will explain more. Is it clear? No question?
No question, sir.
Okay. For part B, we have similar to part A, a system similar to part A, but this time it's located on a slope, and here we have an inclined surface. For this system, when you want to extract the equation of motion in terms of vibration, because the mass of this cylinder will create some initial deflection into the springs, and we should ignore the weight and initial deflection. The equation of motion is similar to the previous part, part A. And here, of course, we have two springs. I mean, using the equation of part A, we can use this equation here, and only here we have one krx, but here because we have two springs, we know that the equation of motion will be 2 times by krx. So the equation of motion is the same, but I will explain how to extract this equation. Here you can see for this system, again, we can write the moment equation about point O because there is no slipping. So similar to the previous part, we can assume that this cylinder is rotating about this fixed point. So we can write the moment equation about this point O. We will have three forces, two forces due to the springs and one force due to the damper. All of them are kx, cx dot related to x, which x is r times by theta, similar to previous part. And it must be equal to the mass moment of inertia about point O multiplied by the angular acceleration theta double dot. So you can write the moment equation about this point, which is the force times by its arm, and the arm is equal to this distance, which is r. So minus kx times by r minus kx times by r, we have two springs, one damper minus cx dot times by r, and again these negative signs are due to the direction of the moment. Here you can see the moment due to these forces are in counterclockwise direction, but the direction of theta double dot is in clockwise direction. If we assume this is positive, So the direction of these moments are negative. It must be equal to the mass moment of inertia about point O multiplied by the angular acceleration. And IO is similar to the previous part, is 3 over 2 or times by mr squared. And then we can substitute and extract the equation of motion. And if you compare with the equation of motion in previous part, you can see the equation of motion is the same, only here we have a coefficient of 2, which is due to we have two springs. So the point here is that this incline or this theta does not have any effect on your equation of motion and on your natural frequency. Okay, any question?
No, sir.
Okay, and for part C we have one beam or one rigid bar with mass m. It has pivoted at point O. Here at this point you can see we have two springs, one with the stiffness 3K and the other one with the stiffness K, and one damper with this damping constant C. We use the degree of freedom theta. As you can see here, this is theta, and the position of the springs are at the end of the springs here, as at the bar, sorry, one here at point, I don't know, for example, point A. Here at point B, we have another spring, and one damper here at point, for example, C. The displacement of point A is this length times by theta, which is equal to L over 2 plus L over 4. The displacement of point B is L over 4, this length, times by theta, because it's rotating about this fixed point O. And the position displacement of point C is L over 4 times by theta. So the force, if you plot the free body diagram and you assume that this rigid bar is rotating in clockwise direction with acceleration theta double dot, and this is the positive direction of motion, this motion will create some force in the springs, and one force due to the spring with the stiffness 3K times by its displacement, which as I told you is L over 4 times by theta. This is the displacement of point B. The displacement, the force due to the damper, which is C times by the velocity of point C. The displacement of point C, as I told you, is L over 4 times by theta. So the velocity is L over 4 times by theta dot. And finally, the force due to this spring K with the stiffness K times by its displacement of point A, which is L over 4 plus L over 2 times by theta. And here you can see that we neglect the weight. Here, this bar has mass m, but we neglect the weight because the weight of this bar creates some initial deflection in these two springs. We neglect the initial deflections, and we will neglect the weight as well. So IO is the mass moment of inertia about the mass center plus md squared, which d is the distance between point O and G. The mass center is located here at point C. So the distance between the mass center and point O is L over 4. So D is L over 4. And we can calculate the mass moment of inertia about point O and write the moment equation about this point. If you write the moment equation, we have three moments due to these three forces. So each force multiplied by its arm, because we are calculating the moment due to this point, about this point. So the moment due to the first force, this one, multiplied by its arm, which is L over 4. The force due to the spring, sorry, due to the damper, which is C times by L over 4 times by theta dot, multiplied by its arm, which is this length, and it's again L over 4. And finally, the moment due to this force, which is equal to the force times by its arm, which is this length, and it's equal to L over 2 plus L over 4. So we can substitute and calculate the equation of motion. It must be equal to the IO times by theta double dot, and all of them have negative sign because the moment due to these forces are in counterclockwise direction, so it will be negative. And finally, by simplifying this equation, you can extract the equation of motion. And if you simplify this by multiplying by 48 divided by L squared, this is the simplified form. And finally, the natural frequency is the square root of the coefficient of theta divided by the coefficient of theta double dot. So this is the equation of motion and the natural frequency for this system. Okay, any question? Is it clear?
Yes, sir.
Okay, so if you don't have any question, we can wrap up this tutorial session.
Thank you, sir.
Okay, thank you and have a good weekend. Thank you. Bye.
Thank you, sir. Bye.